Hey everyone, and welcome to This Explainer. Today, we're setting the stage for a really comprehensive deep dive into the actual mechanics of machine learning. We're going to cut right through the hype and the jargon, look at how these systems literally operate in the real world, and take a model all the way from raw data to a fully active pipeline. It's going to be a fantastic ride, so let's get right into it.
Okay, let's dive into this roadmap. We'll start with a real-world story about a startup called HealthPredict. From there, we'll look at why their specific problem absolutely requires machine learning, unpack all those heavily conflated terms in the AI ecosystem, learn how machines actually learn, and demystify how we prepare the data. Finally, we'll wrap up by seeing a full pipeline in action.
Section 1. The HealthPredict Challenge.
To really ground our understanding today, let's step into the incredibly high-stakes world of preventative healthcare. Imagine a startup named HealthPredict. Their whole mission is to prevent chronic diseases like diabetes before they happen. Now, they have absolute mountains of patient data, right? Age, gender, region, alongside clinical visit metrics like body mass index, glucose levels, and blood pressure. But as you know, just having data is only the beginning. They face a really tough dual problem. On one side, doctors are completely overwhelmed by these complex, raw numeric reports. And on the flip side, patients are lacking clear, natural language health guidance that they can actually act upon without needing a medical degree to decipher it.
So, their hurdle isn't a lack of data. Not at all. It comes down to exactly two primary challenges. Number one, predicting clinical risk reliably and explainably. I mean, they need to know exactly which patient is on the verge of developing diabetes before it happens. And number two, communicating those complex predictive results effectively to non-technical end users.
Moving to Section 2. Why machine learning?
Now, you might be wondering, why can't traditional dashboards and simple rule-based systems solve this healthcare crisis? I mean, why not just build a really nice Tableau dashboard? Well, the truth is, descriptive statistics and data science dashboards certainly provide massive value. They summarize the past beautifully. But they simply cannot calculate future unseen medical risks. Basically, they tell you what already happened, not what's going to happen.
And this brilliantly illustrates the dividing line between traditional data science tasks and machine learning. Traditional analytics give you a static, rear-view mirror look at historical clinical data. Machine learning, on the other hand, gives you predictive power. It takes structured metrics, like blood pressure and BMI, and mathematically calculates the statistical probability of a future clinical event. In a setting where catching a chronic illness early literally saves lives, you don't just need to describe the data, you absolutely must predict from it.
Section 3. The AI Ecosystem.
So in the tech world, terms like AI and machine learning get thrown around constantly, kind of like they mean the exact same thing. But they don't. Let's start at the very top. Artificial intelligence, or AI, is the broadest umbrella term. It refers to the wide discipline of creating systems capable of imitating human intelligence, things like reasoning, planning, and decision-making. But here's the critical takeaway. Not all AI involves learning. For instance, think of a basic rules-based expert system that simply follows hard-coded clinical guidelines to recommend treatments for mild hypertension. That is technically AI, but it is not machine learning. It's just following human-written rules.
Machine learning, or ML, is a specific subfield within AI. Instead of being explicitly programmed with rules, ML algorithms actually learn patterns directly from data and improve with experience. It relies heavily on structured, tabular data, spreadsheets. For HealthPredict, ML is the engine that calculates whether a patient has a high risk of diabetes by mathematically combining those structured columns of BMI, glucose, and blood pressure into a predictive model.
Going one layer deeper, we find deep learning. This is a highly specialized branch of ML that uses deep neural networks, specifically designed to handle massive volumes of unstructured data. We're talking about things like computer vision, speech recognition, and natural language processing. In the context of our startup, HealthPredict, while traditional ML handles the spreadsheets, deep learning would be the tool they use down the road to process unstructured signals, like automatically detecting early anomalies in X-rays or electrocardiograms.
And finally, we have generative AI. Gen AI is a specialization within deep learning utilizing foundational models like transformers. Its unique defining characteristic is right in the name. It doesn't just analyze data or predict numbers. It generates entirely new content. Think text, audio, images, or even code. For HealthPredict, this is the missing piece of the communication puzzle. Gen AI can take those dry mathematical predictions and generate a personalized, empathetic medical report drafted in perfectly natural language. To wrap up this ecosystem breakdown, look at how traditional ML and GenAI compare and perfectly complement one another. Traditional ML gives doctors the high explainability and statistical precision they desperately need from tabular data. But GenAI provides the communication layer, seamlessly translating those rigorous statistics into a conversational format patients can actually digest. Essentially, one detects the risk and the other explains it.
Moving on to Section 4. How exactly does a machine learn?
If ML doesn't use hard-coded rules, how does it figure things out? Well, there are three main methodologies. Supervised learning is when you provide the model with a labeled dataset, meaning it sees the input features like age and BMI and the exact target output, like whether the patient actually got diabetes. Unsupervised learning is when you drop those labels entirely. The model just gets the inputs and has to discover hidden structures completely on its own. And finally, reinforcement learning is an interactive agent that learns purely through a process of trial, error, and receiving digital rewards or penalties.
Now, what's really interesting about this slide is how supervised learning splits into two distinct paths: regression and classification. If HealthPredict wants to predict the exact continuous number of a patient's future systolic blood pressure, say 138 millimeters of mercury, they use regression. But if they just want to assign a broad category, like labeling a patient as either high risk or low risk for diabetes, they use classification.
On the unsupervised side, we have techniques like clustering, which can automatically group similar patients together, like clustering all young patients with high BMI, without any human prompting. Then there is dimensionality reduction, like PCA, which can take, say, 15 complex clinical variables and brilliantly compress them into just two main components so doctors can easily graph them. And of course, recommendation systems, which can suggest tailored fitness plans based purely on what worked for patients with similar unlabeled clinical clusters.
Section 5. Training and preparing the data.
Before we compare models, think about predicting the price of an apartment. It's a great analogy. The size and location are your features, the price is the target, the mathematical procedure is the algorithm, and the internal numbers it tweaks are the parameters. When building these models, you have a choice. Parametric models, like logistic regression, have a fixed, simple number of parameters regardless of how much data you feed them. They're fast and highly interpretable. Non-parametric models, like decision trees, are highly flexible. Their complexity physically expands to capture intricate relationships as you add more and more data.
So the crucial point is finding the balance. If you choose a model that is way too simple, like only using the number of rooms to predict an apartment's price, you get underfitting. It completely fails to capture the real patterns. But if you use an insanely complex tree that memorizes every single apartment in your training set, you get overfitting. It looks totally perfect on paper, but fails completely when predicting a new, unseen apartment. The entire goal of machine learning is generalization, balancing perfectly between these two extremes.
But listen, a model is totally useless without pristine data. This requires rigorous feature engineering. First up, transformation. We normalize numbers using scalars so they're all on the same playing field, and we encode text categories into numbers. Second, selection. We aggressively drop irrelevant variables, like a patient ID number, which obviously has zero predictive value. And third, imputation. If less than 5% of our glucose data is missing, we don't just throw away the patient's record. We intelligently fill that gap with the median value.
I want to highlight one absolutely crucial, highly powerful transformation technique here called target encoding. Imagine a patient file simply says hypertension. Algorithms can't read text, right? Instead of just randomly assigning it a number, target encoding replaces the word hypertension with a mathematical weight that represents the historical average risk. If past patients with hypertension develop complications 70% of the time, the model replaces the word hypertension with the number 0.7. It explicitly captures the statistical relationship inside the category itself. It's a real game changer.
And finally, Section 6, HealthPredict in action.
Let's move to and see how this builds into an end-to-end flow. Phase 1. They ingest the raw clinical data from various clinics right into a data lake. Phase 2. The ML engineers step in, applying all that feature engineering we just talked about, standardizing BMI, imputing missing blood pressure, and applying target encoding to medical conditions. Phase 3. They feed this perfectly clean data into a traditional machine learning model like a logistic regression, which calculates a highly explainable statistical risk score for diabetes. And finally, Phase 4. That dry numeric risk score is passed over to a generative AI model, which instantly drafts a warm, clear, natural language report for the patient. Just like that, raw data becomes a life-saving conversation.
It is absolutely staggering to see how these distinct AI tools, traditional ML for rigid precision and GenAI for human communication, can synergize to solve massive real-world problems. If this combined AI ecosystem can completely revolutionize preventative healthcare, literally giving doctors superpowers and patients real clarity, I want to leave you with this provocative thought. What other highly sensitive, complex industries is it going to transform next? Finance, law, education? The possibilities are honestly endless. Keep exploring, and thank you so much for joining me on this deep dive into machine learning.